So we're going to take a look at evaporation of liquids. It's kind of a unique thing. Normally we think of changes of state as happening at a single temperature. We think of the boiling point of water where it changes from liquid to gas, or the freezing point of water where it changes from liquid to solid as being happening at one particular temperature. Well, evaporation happens at a whole range of temperatures. And so we want to try to get an understanding of how that works. And along the way, we're going to explain vapor pressure as well. So we all know that if we put a glass of water out on a hot day, that water will slowly evaporate. It will disappear, so which means it's going to change from liquid to a gas. So how does that happen? Well, first off, if we look at the sample, let's say that this is water inside the flask here. Which particles do you suppose would change into a gas? Would a particle down here at the bottom end up changing into a gas? Well, probably not. I mean, you're probably talking about particles that are at the surface that will then escape and go into the gaseous state. Now, we want to remember that those particles aren't going to just do this, because normally the particles have attractive forces that are holding them together. Water molecules have very strong hydrogen bonds that hold one molecule to another. So these particles are going to have an awful lot of energy to break apart that hydrogen bond that's holding two molecules together, the molecules together. So these molecules are going to evaporate, have to have a lot of energy in them. So where do they get that energy from? We need to kind of address that idea. Once they get up into the flask, then what's going to happen to them? Well, they can escape out of the flask, right? So we could have particles that would effuse out of the flask. But perhaps we could have particles that bump into the wall of the container, transfer some of their energy to the container, and then either form condensation on the side of the flask, or perhaps even drop back down into the liquid because they've lost that energy. So now they're kind of back into the liquid state and attracted to the other molecules there. So let's take a look at how we might kind of better understand this. So here we have an apparatus where there's a flask that's attached to a U-tube. In the U-tube we have some mercury, and if we put the liquid in, and in this case we have liquid ethanol, if we put that into the container on the left and even out the levels of mercury before we allow the liquid to evaporate, the pressure inside the flask and the pressure outside open to the air, so this would be the air pushing down over here, would be the same. Now, once those liquid particles start to evaporate, they're going to bounce around in there, and the pressure on the left-hand side is going to increase, and that's going to force the mercury down on that side and up on the other side, and that difference, if we measured the height of the mercury, would be the vapor pressure in millimeters of mercury at whatever temperature we were working with. So when would this stop? Would it just keep evaporating? Well, no. What's going to happen is that eventually the number of particles that are going from liquid to gas is going to be equal to the number that are going from gas to liquid. So as more particles evaporate, we're going to get more particles condensing back into the liquid state. And once the number that are evaporating is equal to the number that are condensing, we would be at what's called equilibrium. And the pressure would then stabilize. Now, it's not going to stop evaporating. It's not going to stop condensing. Equilibrium is an idea where there's a balance, and in this case it's a balance between the number of particles that are evaporating and the number that are condensing, but the process doesn't necessarily have to stop. And so this is what's called a dynamic equilibrium, where the particles are continuously going through this process, but there's no net change in the number of vapor particles. For every one particle that evaporates, another one's going to condense to keep that pressure the same. So next, let's take a look at what might happen to this container then if we do a few changes on it. So let's put a stopper on this container here. And again, so we've got particles evaporating, particles condensing, and once we have the number that are equal, we would end up with a certain pressure, right? So pressure will go up to there. What happens if I take that flask now and I make it larger. So let's increase the volume of that flask. And we'll get a larger stopper as well for it. What happens to the pressure now? Well, there's more space up there, right? So more molecules are going to evaporate. We've even got a greater surface area for them to evaporate in. But what we're going to find is when we reach that dynamic equilibrium, where the number of particles that are evaporating is equal to the number that are condensing, the pressure ends up being the same, provided the temperatures are constant. Right? Now, if we were using a real gas here, according to our gas laws, if we increase the volume, pressure should decrease. But this is a vapor. So what happens is as that volume increased, more molecules would evaporate, and you would keep the same pressure as what you had before. Just the opposite would happen if you decrease the volume. Initially, the pressure would probably get a little bigger, but then you'd have more molecules that would condense until the pressure went back to where it was before. So let's try doing this at a new temperature. So now we're going to be at T2, which is going to be greater than T1. So now what's going to happen there? Well, if we thought about our gas laws, we might kind of think that, well, if the particles are at a higher temperature, they have more kinetic energy, they're moving faster. We might kind of think that the pressure is going to increase. And that would be the case. But it's going to increase for a couple of reasons. One, at a higher temperature, you're going to have more particles, or a greater number of the particles that are on the surface are going to have enough energy to overcome the attractive forces and escape into the liquid state. Once they're up there, they're at a higher temperature, so they're going to bump around with more pressure. But again, some of them will lose energy and drop back down into the liquid state. But when we get to that point where the number of particles that are going from liquid to gas is equal to the number that are going from gas to liquid, right? We get to that vapor pressure equilibrium. We're going to find that the pressure has gone up. So at the higher temperature, the vapor pressure of the liquid has increased. Right, now this gives us kind of a clue as to what's going on here. So what we need to do now is to look at our friend the Boltzmann distribution. We call it the Boltzmann distribution is going to give us a visual picture of the actual distribution of energies of molecules in a particular sample of a gas or a liquid or a solid. And remember that when we measure the temperature of something, and that's giving us an idea of the kinetic energy, it's really telling us the average kinetic energy. When you look at a sample of a liquid, the particles in that liquid actually have a whole range of different energies, all the way from 0 up to infinity. So here we have a curve that represents a low temperature, the blue curve, the one that's a little bit higher, and we have a curve that represents a higher temperature, which is the red curve. And then we have this, kind of we can pick a point right here, which is the dotted line, which is the amount of energy, the amount of kinetic energy a molecule would need to go from liquid to gas. Right? So that would be the energy that it would need. It would also need to be on the surface of the liquid. So you can see that in the blue curve, there's a smaller, maybe make that in red, there's a small number of particles that have enough energy that if they were at the liquid, they could change from liquid, or if they're at the surface, they could change from liquid to gas. At the higher temperature, you would now have an additional percentage of molecules that would have enough energy to escape. And so you would then have more molecules that would escape into the vapor state. And again, you would create a higher pressure. Now, if we graph these things, or if we graph the vapor pressure at different temperatures, we're going to end up with curves such as this. So there's four different substances here. One is diethyl ether, and that's the one over here on the left. And so you can see that the vapor pressure of that, which is the vapor pressure is the y-axis, temperature is the x-axis, that vapor pressure, if you chose any temperature at all, that vapor pressure is the highest, which means those particles would have to have the weakest attractive forces, because it doesn't take a very high temperature in order to get those to evaporate and create more vapor pressure. Ethylene glycol, on the other hand, the one down here in the lower right-hand corner, right? That one hardly has any vapor pressure at all until you get up to 60 degrees Celsius. And even then, the vapor pressure is very low. So ethylene glycol must have pretty strong attractive forces where it's very difficult for the molecules to separate from each other. And then kind of in between the two of those, we have ethanol, ethyl alcohol, and water. So you can see based on this diagram, the ethyl alcohol at a given temperature would have a higher vapor pressure than water, which means its molecules must have weaker attraction than the water molecules do for each other. Now, the other kind of significant thing that we can look at here that's going to lead us to our next discussion is the normal boiling point. What happens when the vapor pressure is the same as the pressure of the air around it? All right, so that's a very interesting question that we'll take up in the next video, which will address boiling.